Hello everyone. In this video tutorial I'm going to show you how to design a base plate shear design in IdeaStatica. Actually, base plate is mostly we use it for the moment resisting as well as for the shear design. So we want to consider the base plate just have bearing a axial force. Now we will go to the IdeaStatica, and here is the end plate connection design, and you can select the project based on your requirement. So mine is W section, so I can section. Here is the first part in the design is moment connection, is shear connection. In the shear we don't have shear force and moment. We give a name, and also if you have any description you can write it, and choose the material and the code, the electrode as well. I'm going to create. Now the model is created. This is the dimension of the concrete block, and this is the column. This is a beam, and the load is given by 1200 millimeter, 200 kilonewton in the top location. So in case if you think this is proper, you can first calculate and see how this behave. In case if you have any kind of an arrangement, you can bring it by adding using operation. So for this one, just I want to make some changes on the size of the weld. This is the weld is 10 millimeter, and I want to use 12 millimeter, and this also 12 millimeter. And one more thing is I want to change the load. This is 1200 kilonewton is very less, so usually we think it's about 3-story structure, so we want to make 3000. But in some case there is possibly a loss of shear in the bottom and also moment. We want to add some small amounts of shear and moment, so at least 35 kilonewton in the y direction, and about 35 in the z direction, and some moment is a little moment, 20 in the x, and just 20 in the x is okay enough. So we have this, and we want to calculate this. The analysis completed, but unfortunately the plates, which is mostly this plate from the column, flange and wave, is not passed, and the weld is also not satisfied. The concrete block is also not satisfied because the load which we are giving is quite high. So what we're gonna do is we want to change the column. In previous we should conduct a column design, and column should design, then we will bring the designed column to design the base plate. So we go back to the column. Here we can change the column. Here is the column that 12, 16, and I want to use another column. Let's use 1275, and it's a little larger, so okay, the column is changed. Now we want to change some in the concrete block as well. So we go to the concrete block. In the bottom here is the concrete block foundation. We want to the offset in two direction should be 400, instead of making larger, so then when increasing the area, so the pressure will be less, so that it will satisfy. And next is I want to increase the size of the weld. Now it's going to, instead of increasing list using 12 milli, 14 milli, and also changing the electrode to 18. Now these three parameters, column and weld and block, is changed. Now we want to recalculate. The analysis completed, but still the concrete block didn't pass. So what we're gonna do is we go to back again to this here and change. You can change the concrete, and this is very effective, or you can go to increase this to 500, and this will be okay. Now we're gonna go back again and redesign. So it's still didn't pass. Now the only way is to we want to use concrete with a larger compressive strain. So we change the concrete compressive. Now we wanna rerun again and see how it's work. This is the result, and result is fortunately very economical, which we used almost 80% of the concrete criteria. So now this is the design of this split is completed. So why in the loading I had some shear force moment? Because in practical there is very few examples to have the two depending the both of the column should hasn't moments or shear force. So there is at least some, because the loading criteria or some manufacturing or some other ratio caused to create some shear force and also some moment. So now it's all this criteria is completed and we finished the design. So now we can go to create a report and see. This is the report, and here is the report of my work. So here is everything is passed, and the dimension and analysis explanation, and here is the behavior, and here is the code check, weld check, everything. So now you can go to send it to any kind of this other application to see or edit for your client. And thank you. This is the end of the tutorial. If you have any question, please put in the comment and I will find time to answer you. See you next time. Hello everyone. In this video tutorial I'm going to show you how to design an end plate beam column connection in IdeaStatica software. End plate beam column connection is one of the most commonly used for earthquake resisting structure, which we usually call semi-rigid beam column connection. After moment resisting beam column connection, we have end plate beam column connection. So now let's start in IdeaStatica. We have the IdeaStatica software. You come in the class, you is here, and from here you can use a single beam column and also double beam column connection. So we will first using this method and giving a name. This is called end plate connection, and selecting the design code you want. So I want to use a AISC code 13, and here is different kind of connection. Which one you want? I want to use a single just end plate which is connected to the beam without any stiffener, just with bolt. Create. Now the connection is connected. We can see it is actually in default with this criteria is proper okay, but we want to check the load. This is the load 1, and which is about this is the shear force and this is the moment, and this is also another moment, positive moment and negative moment. So we have these two moments. So in case if we assume this is correct and we want to see this connection will pass the available data or not, we're going to check it first. In case if it didn't pass, then we will bring some changes to the model, to the connection. Now the result is here, and we can see the beam is not suitable for this loading properties, so mostly the flange areas fail. But this is not common when you bring analyze it beam column from another software for design after you designed, because we didn't design first the beam column, so just we are intend to design the connection. The beam is unfortunately unstable and it's fail. So we don't want to change other parameter except this beam. We want to go to this beam, it's member 2, we can go to edit. In edit, here is called shape, you can change shape. This is 16 by 36, so we want to extend a little larger. Let's suppose this one, maybe this one is also it cannot pass. We want to a little larger, that will be good. So now we select it. In case if I go to back, you can see the first one, this 60, the 60 is 400 the height, and the length is 1718, and the thickness is 11 by 11. Now if I go back to the 1645, now the flying thickness is increased by 40 millimeter, so it's exactly better than the previous one, which we about 2 millimeter extend the thickness of line. But we're gonna accept it and we want to rerun and see how it works. Now let's see the analysis completed, and we got a very nice result. Very nice result, but here is two important thing. One is still this is the color seems in a very economical design. This green is very optimal design, and that one is very over least strained design. It's an economical this line, so that means that some instabilities exist. So for this we can add some extra stiffener in the columns, that will be more better. By adding that stiffener, so the cost of the design connection will not increase too much. So we can go to operation and create automatically. Here is called stiffener. So we create a stiffener in this area. Now let's see, it's about cost $100. Now the thickness is 16, so I assume the 16 is okay, and I want to rerun and see how this can change this flange, this beam column flange stress. Now the analysis completed. You can see the color is changed. This color is changed from the yellow color to the green color, so the result is getting better and very acceptable. So now we can go to the check and see in the checking. We can go to the stress contour, and this is the stress contour. More stress is concentrated in this bottom, and we also can go to see the bolt forces. This is the bolt force in top, and also we can see the deformed shape. This is a deformed shape because the loading in the bottom side is very high, so you can see, and this is a deformation. Now we can also see the plastic strain. This is the plastic strain, which is mostly in this area. So for preventing this strain here, you can add some extra stiffener in this location as well. Or instead of adding end plate here, you can add one extra plate here and connect this, make it more stronger. This is depending to your ability and experience, how you can provide a very resisting beam column connection for your structure. So this is the end of the tutorial, and in case if you have any problem, and please put in the comment and I will find time to answer you. In the next tutorial we will use a moment resisting beam column connection. See you next time. Hello everyone. In this video tutorial, I'm going to show you how to design a moment resisting beam column connection in IdeaStatica software. So we usually have two kind of moment resisting beam column connection. One is moment resisting beam column connection with welding, and other is with nut bolt. So both are sometimes also can be composite, and in some area we need to weld, and also some region need to use nut bolt. So we especially we will go to just use the weld connection, and we want to, after the design is completed, we want to verify is this a moment or rigid or not. So moment resisting is rigid. So now we go to the IdeaStatica, and in IdeaStatica you can select any of this class. So I will select this one, and here select in the geometry this option. Here is the different kind of connection, and this is usually called shear connection, and this is called moment connection. So I can use this one or any of them you want, but we at least select the just the this one, which is usually used moment welding. This connection is the most simple connection which we use for earthquake resisting structure. But in some specific, some other based on some code requirement or some special connection, so then we use combined, and we will create some innovation that can provide more stability for that entire structure. So now let's see how this is connected. And we have two member, and also creating stiffness in the which is in the same layer with beam flanges, and we can check this is the first member, and this is the second member, and this is the column using this different cross section. Now we will go to the loading. So this is the loading. We have two load, and this is the shear, and this is the moment. Now in case for the simplicity, we don't have any pre-designed steel beam columns, so we just considering to design the connection. We want to accept this loading and this template beam column. We want to check, is this with this criteria, with this sort of configuration. Let's see, 9mm flange and web is 6mm using E13. It will verify or will pass the this loading or not. In case if it didn't pass, so we will have a lot of option to improve this connection and finally get a verified connection design. So now we go to check, calculate. It take a few moments to finish, and then we will see what we can do. Yes, fortunately this is quite safe, and you can see the plate is any of this plate, the flange wave is passed, and or the well is also passed, the analysis completed. Totally this is safe. So but I want to, this is a very not economical, even it's very cheap, but we want to bring some small changes. Let's bring this to 6mm, and this one to be 5mm, and the same 6mm and 4mm, and the stiffener thickness is 8mm, so it's okay. Now we want to redesign, which we changed in case if you want to use a very lower electrode, so then you can go check it. Now we can see now how it works. Now let's see, it's quite better than before because the 3 mm weld is actually reduced. That will be more economical. Now we're gonna go to hit 30 from 48 to 38, $10 reduced. So this is very good. Now we can go to the check and see how this behave. So the first part is we want to see the plastic strain, and this is the plastic strain, and we can go to the some, and that's 3D is okay, and we can see. So including the plastic strain, we want to see the deformed shape. This is very less because the load is very little, and I want to see the meshing, how, because the IdeaStatica is a finite element method, so they're using mesh principle to design the structure. Now we want to remove the mesh and we want to see the stress strain contour. So here is very little, so there is no, it's not reached to the yield strength. Now we can go to the equivalent stress. So the equivalent stress is very less, and you can see here. Now the next thing is, in case if I want to see exactly this is a rigid connection or not. In case it's rigid connection, that's a moment resisting. It's not rigid, that's not a moment resisting connection. So what we're gonna do is we want to go to back to the design, and in the design we want to consider the stiffness design. So when you go to the stiffness design, the structure will return back and it come back to the default, and we will calculate again using the stiffness. So the stiffness calculate, and it will start stiffness. This take a little time, and it will produce a stiffness rotation curve, and you will analyze to see this is a moment rigid beam column connection. Now the stiffness analysis completed, and now we can go to see in the check. In the check, we want to see the stiffness. Here is called rotational stiffness, and we can go to check it. Here is the curve. And now this curve is actually our structure. So this is a moment rigid connection. In case this curve comes to this area, we call semi-rigid, and in this area it's allowable stiffness. So this is what we have. This is very large. So now we got the structure is 88, so quite large. So this is a middle point, and this is the lower point, and this is the exact connection resistance, so the moment and the rotation. So the moment rotation is very large, so moment rotation is less, the moment is high, that will be rigid. In case the rotation is very large and the moment is less, so that will be semi-rigid. You can see here we can also go to the report and create a report, and there is more information, and also here is more information regarding to the project, to the material, to the check. And now here is the same way. You can see bending resisting and initial rotational stiffness, and this is second rotational stiffness and rotational deformation. Now here is the one thing that's called the limit value for rigid joint, and you can see Two is the lowest rigid uh, connection. So for the detailing, you can select all, or also can select other things, especially the theoretical background. You will see more information. Now this is the end of the tutorial. If you have any question, please put in the comment and I will find time to answer you. One more thing, and you can send to the DXF file and you can create the detailing there. See you next time. Hello everyone, in this video tutorial I'm going to show you how to design a shear connection. So in IdeaStatica, the shear connection we consider there is a lot of shear connection which we can perform in IdeaStatica, such as pore line connection or as any sort of elements, but specifically we will consider the beam column shear connection. So we go to the IdeaStatica in the project and we search class and geometry and design. We can select shear and give a name. It's called shear connection, and using this American code create. Here is the model. So first of all, let me see. We have one member column, and this is beam, and this is the loading. So why we call shear connection? Because this kind of connection cannot bear the moment. Maybe it can later, but it's not a moment resisting structure. So usually in practical we have so much such kind of connection. Now in the this connected is using with a T section. Let's go selecting this one and going to the that's called clit, and you can see this is a T section. I'm going to edit. Here is, so the thickness is 17 and the height is about 100. So without any change, I want to design this connection applying this force. So now I'm going to calculate. The calculation is completed and we want to see the result. So this is the result, and it's totally with a gray color, so that means the connection is quite not economical, and you can see we couldn't use larger the plate, so this plate is very large. The first thing is I want to change this plate. Let's go to back again, and here, and we go to the edit here, and we used the height is 100 and 12 by 15. If I go to back here, and he's exactly here. So what I want to do is I want to use a little smaller one. Let's see. This 12 is the height is 100, and I can use a little larger one, but instead the flange and whip thickness should be smaller. Let's use this 10. This is, you see, it's the same but 30 millimeter, and this also from 17 we brought to 13 4 millimeter, and it's smaller. If I go to select one more, let's see, 18 is the 18 is 11, and this is better, and I'm going to OK. Now you can see some changes made here, and one more thing is I'm going to change the size of that clip. So we wanted that clip should cut a little larger, and it should be about 180. This is 180. So we cut it a little larger. And the next thing is I want to reduce or make smaller the size of these bolts. So here is the bolt, and I want to use the 1/2, the same material. So this one, and selecting this, also using is here. Now we change these two parameters, just as the clipped area and the nut bolt. So now we want to run again. Now, so it's called bolt or too close together, because this bolt is actually it's very close together. It means here is the space is very high, so we want to change that one to have a little deeper height. This one should be a little larger, so I'm going to back to here to select another one. Even we can go back to bring this bolt a little closer, and here is the first bolt. This bolt, it's not 40, and I want to using 30, and this is also 30. This is the longitudinal. This is okay. If I go to Control Z, and it will work again, but in here I want to make it 30 millimeter space between the this direction. Now you can see it's correct, and we want to recheck it again by calculation. That was the reason which the analysis not completed, because it was seems very close to this location. Now the analysis completed 100%, and the plate and the bolt, everything is used properly, and the cost is reduced to $50. So this is acceptable. Now in case if didn't, one problem is here actually, so this is not right, so because the bolt is very close together, but the result is okay. I want to change that one as well. Now what I want to do is just go to back to this, and instead of this one I want to change this one, should be a little larger, and that 833, and I can select, and that at least this one, it's also a smaller one, and we're gonna go to 12 and 12, 25. This is also good, and let me check one more. This is 10, 20. If I use 35, this is very good. Okay, now we have a large area, because we not build this dead area, and it's very good. Now what I want to do is I want to just change this spacing and to back to 40, and now it seems better. In case if I want to make it this in a positive direction, that can be 45, and this also can be 45. Now we have a lot of space. This one is not, and I'm going to back to this one, should be 40, and this one should be 50. Sorry, and this one should be 30, that should be 50. No, let this be 40, 30. Now it's better. Now the changes not too much, and I'm going to make this one 35, that one, and this one should be make 40. It's better to make 45. So later this is okay. Now we can or that 40 is okay. That 40 is okay, and there's no interaction together, but still is there. That 45. Okay. The problem is it should be center to center. I go to back here to this element, and I want that transfer in both direction. This area is large and this area is smaller. If I go to this direction, we can see so some because the web is in this direction, so this will be a little less. So in case we should create another build T section, that will be more proper. Now we can go to calculate again. Now it cost $90, and the result is quite acceptable. So we can see everything is properly designed. Now we can go to check and see some such as the pull force, and this is the pull force. One is in tension, one is in the compression, and also equivalent stress behavior. So this is it. Okay, now this is the end of the tutorial. If you have any question, you can put it in the comment and I will find time to answer you, and then you can create a report here. See you next time.